Hey everybody, and welcome to this session on Introduction to Continuum Mechanics. This is basically the last session of the first module on Introduction to Continuum Mechanics, and for the next session, we move to the third chapter of the book, which is basically about the root of the strain and displacement. So in this session, we're going to introduce the spherical coordinate system, and then we try to calculate some of the basic operations, tensor calculus here in the spherical coordinate system. So for this, I prepared a kind of figure here where we have our, x, y, and z coordinate system here. And we have a sphere here, so I tried to put two kind of ellipses here. So to illustrate that we are dealing with a sphere here. And as you can see, the book also put small sphere here and referred this to point P. So if I have, for example, a vector here, like R, and if I project this, let me just switch to another color. So if I just project this on the XY plane, so as we already said, we have this, let's say, ER in this direction. So it is in the direction of increasing R. And then we have theta. The theta is basically increasing in this direction. Or let me just indicate this by another color. Maybe make this one. So this is theta. Therefore, we have this theta increasing in this direction. This is E theta. And phi is basically increasing in this direction. Therefore, we have phi in this direction. So if I just look at this sphere or this particular ellipse from this point of view, from here, for example, so I will get something like this. So I have kind of circle, then I have a coordinate like this. So the vertical axis is z, and the horizontal axis is basically r prime, not necessarily. So here, this is r prime. This is r prime. For example, is the projected of r on the projected vector of r on xy plane. So I just remove this. So if we have this, so we have this point P in here, for example, and then we have this R in here, and we have our unit vectors like E R prime, and then we have E Z in here. And as you know, we have this ER, which is increasing in this direction, and E theta is perpendicular to ER. So we have E theta in this direction. So we have also, let's say, if this is theta in here, so this is basically theta, and this is also theta. Perfect. So the position vector for the spherical, the position vector for the spherical coordinate system is the same as, let's say, polar coordinate system. So we have r is r, e, r. And when we want to find dr, so we basically have dr, er plus r, d, er. And we desire to find this der. So let's call this figure. This is figure 1, and this is figure 2. So from figure 2, you can see here that if we decompose er prime and ez in e theta and er a direction, so we get something like e r prime cosine theta plus er prime sine theta. So if I just project this er prime here, so I have, if I can just zoom out this bit. Okay. So you can see here that we have er prime here, cosine theta. So it gives this e theta here. And if I have e r prime sine theta, this is er. And also I have, for the other one, for ez, I have minus ez sine theta plus ez cosine theta. So I have ez. So if I project this by minus sine theta, it will give this the component of ez, the direction of e theta, and it is in the opposite direction of e theta. So that's why we put a minus here. And then I have ez cosine theta in the it gives the the component of ez in the direction of er. So basically, this will give e theta components, and this will give e r component. So therefore, we have something like e theta is equal to cosine theta er prime. So I switch this er prime here, so the unit vectors after the expression for the sake of consistency, minus sine theta ez, and for er I have sine theta er prime plus cosine theta ez. So now I can calculate der, which is required for this expression here to calculate dr. So I have sine theta. So if I just differentiate with respect to theta, I get cosine theta d theta er prime plus now sine theta, and we have to differentiate with this. So we have d er prime plus, and then we have cosine theta, so it is minus sine theta d theta ez plus cosine theta d ez. And this term is basically 0 because we already discussed this in the previous session that ez does not change. So it is 0 here in this figure. So basically what we get here is cosine theta d theta er prime minus sine theta d theta easy. So this is nothing but e theta from here. Therefore, we have d theta e theta plus sine theta d er prime. So now we have to find d er prime, but let's also let's calculate d e theta as well. So it becomes minus, because this is cosine, so minus sine theta d theta er prime plus cosine theta d er minus cosine theta d theta easy minus sine theta e d easy, and this term is 0. So basically this term here is minus e r. So if we factor out this minus sign here, you get this er in here. All right, so we have minus d theta er plus cosine theta d er, and that's it. All right. The er prime. So we have to calculate this d er in here and also here. So to do so, we look at this is spherical. This is spherical coordinate system from the top view. So from this side, we look at it. So we have this x and y in here. So I have this x and this y in here. And you can see that y is increasing in this direction. So we have r prime. So phi is increasing in this direction. So this is d phi, for example. This is er prime. This is e phi. This is e phi plus d e phi. And this is er prime plus d er prime. So it is like the spherical coordinate. It is like the polar coordinate system. And if you recall from polar coordinate system, so recall from polar coordinate system, that DER was basically d theta e theta. So if we map this into our prime phi coordinate system, so we get something like d er prime is equal to d phi e phi. So we now have der prime based on d phi and e phi. So I can write d, maybe write it with another color, d e r is equal to d theta e theta from here. This is the er. This is what we had here, d theta e theta plus sine theta der prime. So instead of der prime, so we have plus sine theta der prime. So instead of this, I'm going to write, or maybe it's better to write it. So d prime. So from here, I call it, let's say, star. So from a star, I have d theta e theta plus sine theta d phi e phi. And we also have dE theta from here. So I have minus d theta er plus cosine theta d er is equal to minus d. So I substitute this d er prime here from star. So we have minus d theta er plus cosine theta d phi e phi. All right. So we have der and de theta, but what about d e phi? We have no idea about it. So again, from polar coordinate system, so recall from polar coordinate system that we had d e theta was equal to minus d theta e r. So if we map this again, r prime and phi, so we get something like d e phi is equal to minus d phi er prime. So I call this maybe square. And we have d e phi is equal to minus d phi and er prime here. And er prime is basically something that you can find from here. So you have er prime, you have to find the components of e theta and er in the direction of er prime. So e theta is basically the cosine times the cosine theta, and here you have er times the sine of theta. So this will give the component of er prime here. So from figure 2, we have er prime is cosine theta e theta plus sine theta er. All right. And great. So we have minus d phi times cosine theta e theta plus sine theta e r in here. And then we have d e phi is equal to minus sine theta d phi. So I multiply this with this and that. E r minus cosine theta d phi e theta. And this is the expression that we need in here. So we had three important expressions here. So let me just okay, we had this in here, and we also had this one in here, and we also had this one in here. So these are critical to calculate some of the operators, some of the results for the operators in this spherical of the tensor operators in the spherical coordinate system. And now we can simply calculate dr here because we have der now. It is already given in here. So dr is basically dr er plus r d theta e theta plus r sine theta d phi e phi. And this is also very important. All right, so now we calculated all the necessary ingredients that we needed for the tensor calculus and spherical coordinate system. So let's continue with the first operator here, which is the gradient of a scalar field. So is del f. And as you know, f is basically a function of r, theta, and phi. So we utilize the same strategy in our previous sessions for the polar and cylindrical coordinate system. So we have our df, dr, so this is equal to the del operator, so the differential of f with respect to r is del f here. Therefore, we have df is equal to del f, the gradient of f, the dr. So we don't know what are the components of this del f, but we know it is a vector. So del f has a component in r, so del f r er plus del f like theta e theta plus del f phi e phi dot, and the rest goes here. So we have dr, so dr from here we already calculated it, so we have dr er plus r d theta e theta plus r sine theta d phi e phi. Therefore it becomes del f r dr plus del f theta r d theta plus del f phi r sine theta d phi. I'll call this 2, and then I have df. I don't know if we had 1. Maybe call it 1. Okay, so df so f is a function of r theta and phi, so df is partial derivative of f with respect to r dr plus partial derivative of f with respect to theta d theta plus partial derivative of f with respect to phi d phi, and I call this 2. So from 1 and 2, so if I compare 1 and 2, or maybe it's better to say compare 1 and 2, so what you get is del f r is equal to partial derivative of f with respect to r, so you basically compare this with this, this with this, and this one with this one. And then we have del f theta is 1 divided by r. You have a r here. So partial derivative of f with respect to theta. And finally we have del f phi 1 divided by r sine theta. So we have it here. Partial derivative times water derivative of f with respect to phi. And that's it. The gradient of a scalar field is a vector in this form. In this form, and the components are here, are given here. All right, so let's calculate the gradient of a vector field. So here, v is a function of r, theta, and phi, and also it has a component of vr, which is also a function of r, theta, and phi, er plus v theta, which is also a function of r theta and phi, a theta plus v phi, also a function of r theta and phi, e phi. All right. So I have dv, also dr gives del v here, which we know is a tensor. It's a second order tensor, or simply a tensor. Therefore, I can write this as dv is equal to t dr, and this t is nothing but t dr, and dr is already here. So I have dr, er plus r d theta, e theta plus r sine theta d phi e phi. So I have dr t er plus r d theta t e theta plus r sine theta d phi t e phi. So here you have ter, so I have ter, and if you remember, we had this tei, so we had tji, ej. It was just transforming this ej unit vector under this transformation to another coordinate system. So you have ter is tj rej, where this j is basically r theta and phi. So you have this as TRR ER plus T theta R E theta plus T phi R E phi. We also have T E theta in here. So we have T J R, sorry, J theta EJ is equal to T R theta ER plus T theta theta E theta plus T phi theta E phi. And then we have T E phi, which is T J phi E J, which is T R phi E R plus T theta phi E theta plus T phi phi E phi. So now we have these kind of equations here, and we also have this in here. So I call this 3 and I call this 4. So if I plug in 4 in 3, so I would get something like dv is equal to, so I have dr in here, so I have dr times this in here, so this is TRR plus T theta RE theta plus phi RE phi, and then I have RD theta in here times this TE theta here plus, and then I have this R sine d phi, so I have R sine theta d phi times this TE phi, which is here. So I pause the video and write these things. So now I copied this TR, T theta, and T phi from here, and I plug them into this expression for dv. So I have this expression here. So I expand it. I pause the video and write the expanded form, sorry. So now I expanded this dv here, and I also have my dv from here. So I call this 5 maybe. So from 5, I have dv equal to, so because v is a function of r, beta, and phi, and each component of v is also a function of r, beta, and phi. So I'm gonna have something like dvr er plus vr der plus dv theta e theta plus v theta d e theta plus dv phi e phi plus v phi d e phi. And here we already calculated dE theta, DER, and dE phi here. dE phi, dE theta, and DER. So we only need to calculate dVr, dV theta, and dV phi. So I have dVr, so Vr is a function of r, theta, and phi. So I have partial derivative of Vr with respect to r dr plus partial derivative of Vr with respect to theta d theta plus partial derivative of Vr with respect to phi d phi. dV theta is partial derivative of V theta with respect to r dr plus partial derivative of V theta with respect to theta d theta plus partial derivative of V theta with respect to phi d phi, and we have dV phi is equal to partial derivative of v phi with respect to r dr plus partial derivative of v phi with respect to theta d theta plus partial derivative of v phi with respect to phi d phi. So we have this set of equations here. So I have here, I call this 6, for example. So now I can have my dv here. So I plug in these expressions from this set of expressions into this expression to get dv. So I just write it. I just pause the video and write the whole expression. So now I have my dv here, and I need to further simplify this because I have er here. I have also er here and here. So now I rearrange all the terms here in this form, and I call it 7. Now I need to compare this 6 expression here and this 7 here. So if I compare, so I will get TRR, for example. So I have TRR dr is equal to, here I only have dr here. So this is partial derivative of VR with respect to R. Then I have, let me just, this here. So then I have my TR theta is 1 divided by R partial derivative of VR with respect to theta, V theta. And finally I have TR phi is equal to 1 divided by R sine theta partial derivative of VR with respect to phi minus V phi sine theta. Then I have my T theta R partial derivative of V theta with respect to R. Then I have T theta theta is equal to 1 divided by R partial derivative of V theta with respect to theta plus VR. And then I have T theta phi 1 divided by R sine theta times partial derivative of V theta with respect to phi minus V phi cosine theta. And then we have T phi R is equal to partial derivative of V phi with respect to R. T phi theta is 1 divided by R partial derivative of V phi with respect to theta. And then I have T phi phi, which is equal to 1 divided by R sine theta times partial derivative of V phi with respect to phi plus VR sine theta plus V theta cosine theta. And so to calculate del V, you need to put this TRR, TR theta, TR phi, T theta R, this theta theta, and theta phi, T phi R, phi theta, and then phi phi into a matrix form, and you get the tensor for the second order tensor, or the tensor for the gradient of V. Great. So now we have the divergence of a vector field. So the divergence of the vector field is basically the summation of the component of, or it is the trace of del V. So it is the summation of all the diagonal components here. So divergence of V is the trace of del V, which is equal to partial derivative of VR with respect to R plus 1 divided by R times partial derivative of V theta with respect to theta plus VR plus 1 divided by R sine theta times partial derivative of V phi with respect to phi plus VR sine theta plus V theta cosine theta. So next we have the curl of a vector field. And for this, because the curl is basically 2 times the dual vector of the antisymmetric part of this del V here. So I prefer to do it in maple.
All right, so here we're going to use maple to find the curl of a vector in a spherical coordinate system. And to do this, I use the linear algebra package here in maple. And you have to remember that I am using the linear algebra or matrix algebra here to calculate this curl V in a spherical coordinate system. But these are all tensors. I use the matrix algebra because the calculus is more or less like the tensor algebra, and it is fairly easy to implement in Maple. So here I load the linear algebra package here, and I start by calculating the different components here in these lines of the gradient of the vector v. So I refer to the gradient v as del v operator here, del v start here. And I put them into a matrix like this, a 3x3 matrix. So I start with TRR, and as you see here, VR is a function of R, theta, and phi. And this actually goes with V theta here, and also V phi in here. So I load the rest of the first row components here, TRR, TR theta, and TR phi. And then I go to the second row here, T theta R, T theta theta, and T theta phi. So I have the second row here, and then I go to the third row. So T phi R, T phi theta, T phi phi. So this is the third row. So I put them all together into a matrix. Then I have my del V here. So I had a vector, and I applied the del operator here. So I expect a second order tensor, which is here. So to find the curl of a vector, you have to find its dual vector and times it with 2. So 2 times the dual vector here. And the dual vector is necessarily the del V minus the transpose of del V divided by 2. So if I do this, I will get an anti-symmetric or skew symmetric kind of tensor here, where this can be characterized only by a vector, because, for example, this component here is just symmetric, is the same as this one, this component here, but it is just multiplied by a minus, so it is just the symmetric part of this component. So I have 1, 2. So here it gives the third component of the vector of the curl V here. So it is E phi, and 2, 3 here gives the first component of the vector, so it is ER, and this one is basically the second component of the vector for the curl V. So it is E theta. And essentially you know that if you have a vector and you put it into, if you apply the curl operator on it, you will get you will get another vector.
Next topic is the divergence of a tensor field. So if you remember, the book actually defined the divergence of a tensor like this. So we have a divergence of a tensor, second order tensor, times A is equal to the divergence of T transpose A minus the trace of del A T transpose for any vector A. And we already mentioned that the book uses this kind of expressions for the definition of some of the tensor calculus. And here, since we have the divergence of a tensor field, we know that its order is decreasing by 1. So we will deal with a vector finally. So we'll have a vector which had 3 components, one for r, another for theta, and another for phi. So let's suppose that A is equal to, here, A is equal to ER. So the divergence of T for the R component would be divergence of T transpose. This is ER minus trace of del ER T transpose. So we first start by the divergence of this expression, and then we find del ER. We find its product by T transpose, and finally we take the trace and we subtract this term from this term. So we have TER, we already discussed this. This is equal to JR J, which is equal to T, and J is obviously R, theta, and phi. So it's a dummy index. So we have T E R R E R plus T theta R E theta plus T phi R E phi. So T transpose ER is nothing but T R R E R plus, we swap this subscript here, TR theta E theta plus T. This is R phi E phi. So this is like rated with another color. This is VR, this is V theta, and this is V phi. So the divergence of T transpose ER is nothing but something we already calculated here. So we have this partial derivative of TRR respect to R plus 1 divided by R partial derivative of TR theta with respect to theta plus 1 divided by R sine theta partial derivative of R phi with respect to phi plus 2 times TRR divided by R plus TR theta cotangent of theta divided by R. Maybe I call this, so we had 7, I call this 8, and we say here we got this from 8. So next we have ER. So I have 1 ER plus 0 E theta plus 0 E phi. And again here we have something like this is VR, V theta, and this is V phi. So del ER, we already calculated this, so it is 0, 0, 0, 0, 1 divided by R, 0, 0, 0, 1 divided by R. And you can just calculate it from here, this expression here. So we have T transpose. So I put T transpose also here. So I have my T here. So I have T transpose. I swap the rows and vectors. So I have TRR, T R theta here, T R phi here, T theta R, T theta theta, theta phi. This is T phi R, T phi theta, and this is T phi phi. So if I calculate this, so rows and vector, rows, columns, so this is 0, 0, 0, T R theta divided by R, T theta theta divided by R, phi theta divided by R, T R phi divided by R, T theta phi divided by R, T phi phi divided by R. So the trace of del ER T transpose becomes T theta theta divided by R plus T phi phi divided by R. And basically the divergence of T for the R component becomes partial derivative of T R respect to R plus 1 divided by R partial derivative of R theta T R theta with respect to theta plus 1 divided by R sine theta partial derivative of T R phi with respect to phi plus 2 times T R divided by R plus T R theta cotangent theta divided by R minus T theta theta divided by R minus T phi phi divided by R. Next, we select A as E theta. Therefore, the divergence of T theta component is the divergence of T transpose E theta minus trace of del E theta T transpose. So here TE theta becomes TJ theta EJ and is equal to TR theta ER plus T theta theta E theta plus T phi theta E phi. And the T transpose obviously is T theta R here, swap the subscripts, plus T theta theta E theta plus T theta phi E phi. And this is nothing but VR, V theta, V phi. Therefore, we have the divergence of T transpose E theta is equal to partial derivative of T theta R with respect to R plus 1 divided by R partial derivative of T theta theta with respect to theta plus 1 divided by r. 1 divided by r sine theta, partial derivative of t theta phi with respect to phi plus 2 divided by rt theta r plus t theta theta cotangent. Oh, sorry, t theta theta cotangent theta divided by r. Next we have e theta, which is 0 e r plus 1 e theta plus 0 e phi. And of course, this is VR v theta, and this is v phi. So we have del ER is equal to 0 minus 1 divided by r, 0, 0, 0, 0, 0, 0, and this is cotangent theta by r, and then we have t transpose, which is t r theta r phi r theta 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 phi theta r phi theta phi, and this is phi phi. So this is equal to minus t r theta divided by r minus t theta theta divided by r t phi theta divided by r, 0, 0, 0, and this is cotangent theta divided by r t r phi cotangent theta divided by r t theta phi cotangent theta divided by r t phi phi. And now we have the trace of this. So the trace is basically summation of the diagonals. So this minus t r theta divided by r plus t phi phi times cotangent theta divided by r. Therefore, the divergence of t, the theta component, is partial derivative of t theta r with respect to r plus 1 divided by r partial derivative of t theta theta with respect to theta plus 1 divided by r sine theta times partial derivative of theta phi with respect to phi plus 2 rt theta r plus theta theta cotangent theta divided by r plus dr theta divided by r minus t phi phi cotangent theta divided by r. So next we have a is equal to e phi. So the divergence of t phi becomes the divergence of t transpose e phi minus the trace of del e phi t transpose, and t e phi is t j phi e j, and j is of course r theta and phi, so this is t r phi e r plus t theta phi e theta plus t phi phi e phi. And then we have the t transpose e phi is equal to t phi r e r plus t phi theta e theta plus t phi phi e phi. And this is, of course, VR, V theta, and this is V phi. All right. So I have the divergence of T transpose E phi is partial derivative of T by R with respect to R plus 1 divided by R partial derivative of T by theta with respect to theta plus 1 divided by R sine theta partial derivative of T phi with respect to phi plus 2 times T phi R divided by R plus T phi theta cotangent theta divided by R. Next we have E phi, which is basically 0 ER plus 0 E theta plus 1 E phi. And here I have del E phi here, so it is 0, 0 minus 1 divided by R, 0, 0, 1 divided by R cotangent theta 0, 0, 0. And I have here the T transpose T R R, R theta, R phi, theta R, theta theta, theta phi, T phi R, phi theta, T phi phi, which is equal to minus T R phi divided by R T theta phi divided by R minus T phi phi divided by R minus 1 divided by R cotangent theta T R phi minus 1 divided by R cotangent theta T theta phi minus 1 divided by R cotangent theta T phi phi, and the rest are 0. So now the trace is the summation of the diagonals. So the trace of del E phi T transpose is minus T R phi divided by R minus cotangent theta divided by R T theta phi. So we have the divergence of T, the phi component is partial derivative of T phi R respect to R plus 1 divided by R times T phi theta respect to theta plus 1 divided by R sine theta partial derivative of T phi phi with respect to phi plus 2 times T phi R divided by R plus T phi theta cotangent theta divided by R plus T R phi divided by R plus cotangent theta divided by R T theta phi. So next we have the Laplacian of a scalar field. So if you remember, we had del 2f, the Laplacian, and f is a scalar field, of course, is equal to delta del f, which is basically this del operator here. Del dot is the divergence operator, so it is the divergence of del f, and del f here is a vector. So we have the divergence of a vector. So it is equal to the divergence of this del f. So this del f we already calculated here, the gradient of a scalar field. So we already have it here. So it is this vector with these components here. So the divergence of partial derivative of f with respect to r, e r plus 1 divided by r. Derivative of f with respect to theta, e theta plus 1 divided by r sine theta. Partial derivative of f with respect to phi, e phi. So now we have this as VR, this is V theta, and this whole is V phi. So now we have the partial derivative of f with respect to r, the whole with respect to r, plus 1 divided by r. Partial derivative of 1 divided by r, partial derivative of f or with respect to theta, the whole with respect to theta, this is V theta, plus 1 divided by r sine theta, partial derivative of V phi. So it is 1 divided by r sine theta, partial derivative of f with respect to phi, and the whole with respect to phi, plus 2 divided by r, partial derivative of f with respect to r, plus 1 divided by r, partial derivative of f with respect to theta, cotangent theta divided by r. So now, if we simplify it, we get second partial derivative of f with respect to r plus 1 divided by r squared times the partial derivative of f with respect to theta twice, plus 1 divided by r squared sine squared theta times partial the partial derivative of f with respect to phi twice, plus 2 divided by r, partial derivative of r of f with respect to r, plus cotangent of theta divided by 2, partial derivative of f with respect to theta. Alright, so next we have the Laplacian of a vector field. So here we have the del to v for this vector v here. So I just put this arrow here to indicate that this is a vector. So we use this definition from the book, that it is equal to the del of divergence v minus curl of v. So we already indicated that this is a vector and this is also a vector. So here we have a vector. The divergence of a vector field is a scalar field. We already know that the divergence actually degrade the order of the tensor you have. So it will be a scalar field here, and the del of a scalar field is already a vector field. So vector minus vector gives a vector field here. So we expect to get a vector field here. So we have del VR, theta, and phi in here. So let's get started by the divergence of V. So we already calculated this previously, but I can say that the divergence of V is already given in equation 2.35.26 of the book. And here we have the del of the divergence of V. So this is this divergence is a scalar field. So if I write it down here, I have something like del of partial derivative of VR with respect to r plus 1 divided by r, partial derivative of v theta with respect to theta plus 1 divided by r sine theta, partial derivative of v phi with respect to phi plus 2VR divided by r plus v theta cotangent theta divided by r. So this is our scalar field f in here. And you already know that del f actually comes from equation, let me just put this parenthesis here. So it comes from this equation, let's say 235.36. And here we have del f. So del f from this equation here is equal to the partial derivative of f with respect to r, er, plus 1 divided by r, partial derivative of f with respect to theta, e theta, plus 1 divided by r sine theta, partial derivative of f with respect to phi, e phi. So as you see here, we have a vector field here. So now instead of just putting f in here, we have to put this whole this nasty kind of equation here. So this is equal to the partial derivative of f, which is here. So from here, so I just copy and paste this one. I close the parentheses, and then we have er plus 1 divided by r partial derivative of, again, f with respect to theta. So I open up this parenthesis here. Then we have e theta here plus 1 divided by r sine theta partial derivative of f with respect to phi in here. Open the parenthesis and then close it here. And this is e phi, of course. So if we further simplify this, we'll get something like second partial derivative of VR with respect to r squared minus 1 divided by r, partial derivative of theta with respect to theta plus 1 divided by r, second partial derivative of v theta with respect to r in theta. So all of these actually comes from here. So we have we differentiate this first term here with respect to r, then plus, so we have this 1 divided by r, so it becomes minus 1 divided by r squared here. Then we have this partial derivative, so we have this partial derivative of v theta with respect to theta, so it goes here, plus 1 divided by r, and now we take this term, the derivative of this term with respect to r. So we have this equation here. So I pause the video and write all the equation here. All right, so now we have all the equation regarding this part, the divergence of V here. So it starts from here, it goes down here, and you see that we have an ER, E theta, and E phi component here. I hope I haven't missed anything. So, but you can always check, and also you have the book by yourself. So let's continue with this term here. The curl of V we already calculated, but now we want to calculate the curl of V. Okay. So if I just rewrite this, so I just write everything with another color. So curl of V, according to the equation in the book, is something like V phi cotangent theta divided by r plus 1 divided by r, partial derivative of V phi with respect to theta minus 1 divided by r sine theta, partial derivative of V theta with respect to phi er. So this is the first component, er. And next we have this 1. Let me just put this in here. So 1 divided by r sine theta, partial derivative of er with respect to phi, v r, minus 1 divided by r, partial derivative of r v phi. So you have to expand this with respect to r, and this is e theta component. And finally, we have 1 divided by r, partial derivative of v, rv theta with respect to r, minus 1 divided by r, partial derivative of er with respect to theta, e phi. Perfect. So now we have the curl of v, but we now have something like a new kind of vector here, where I call this as new VR. This is as, let's say, new VR. We also have this new V theta, and we also have this as new V phi. So again, when we calculate this del cross del V, we have this vector, which is the whole vector here, this whole vector here. So instead of v phi, we have to put this new v phi here. So I write the first thing, the first term. So I have I have the 1 divided by r cotangent theta. It is here. So I have then v phi, and I have to put this new v phi here. So maybe instead of, no, I think that's fine. So this is the v phi here. So I have to put this, let's say, 1 divided by r. So I have to copy and paste this from here. So copy and just paste it in here. So I have my first term here, then plus 1 divided by r. So I have the partial derivative of v phi with respect to theta. So again, I paste this v phi from here, again, paste it here. Then I have minus 1 divided by r sine theta. Now we have the partial derivative of v theta with respect to phi, where this v theta is basically this v theta here. Perfect. And now we have this er completely here. Now we need to simplify this further, but let's write e theta and e phi as well. So I pause the video and substitute this new VR, v theta, and v phi into my expression. So now I have completely my equation for the curl of curl v here. I call this maybe 10. And I call my previous equation here, which was the del of divergence of V, here as 9. And finally, I will have the Laplacian of V is equal to 9 minus 10. I think that might be a good idea, just to put everything into Maple, so you will see how everything goes with a symbolic kind of code.
All right, so here we are with the Laplacian of a vector field in the spherical coordinate system here. So this is the equation from the book. So as I already said, the book actually utilizes this kind of equations to find some other expressions regarding the tensor calculus. So here, as we already saw, so here I restart everything, and here I form the different components of the of the tensor for del v. So because I wanted to calculate the curl and the divergence based on this del v here. So I have del v here. So I know that the trace of this tensor is basically the divergence of v. So if I do this, I will get something like this, and the divergence of the del of the divergence is basically this operator here from the book. We already saw this. So I put it into matrix form to distinguish between the ER. So the first component here is from here to here is basically let's say the ER component, and this one from this gamma to here is E theta, and this component here is E phi. Alright, so now we have the del of the divergence of V, and then we have the curl of V. So we already mentioned that the curl is basically the is equal to 2 times the dual vector of the del V tensor. So if I put it into a vector kind of form, so I have 1, 2, and 3 component here. So you can see them here. Then I have the curl of curl V. So I use this curl V2. So this is curl V1, and this is curl V2. So this is del of this is the curl of the curl V, but this one is just curl V in the vector form. So I use the substitute here, and I use substitute VR because, as I already said, now we have to put this, for example, instead of VR here, instead of we have to use, for example, this component here as V theta, for example, and put it into here, and take the derivative with respect to phi, and then minus V phi. So instead of V phi, I have to use this component of V phi here. So I use the substitution or subs here in Maple, and I put everything into curl V. So I get something like this. And then I have my final, let's say, calculation here. So I have the del to V is the del of the divergence of V minus curl of V, curl of the curl of V, which is basically this equation here. And the first component, as we said, we expect a vector. The first component is this, second component, and third component. And this actually recaps all the necessary ingredients that you need to go further into the third and the fourth chapter, as well as chapter, I guess, 7 for the basic equations and basic laws and mechanics. So hope to see you guys later in the third chapter.